Hello, and welcome back to a video series on MAT 1033 Intermediate Algebra. My name's Sean Perry. This is video number 33 in the series, an introduction to complex numbers. So as part of building some motivation for the complex numbers, let's briefly consider the questions that produced the negatives and the rational numbers, the fractions. What we wanted to do is fill in this box. 1 plus what would get me back to 0. Now, as long as we limit ourselves to the positive numbers, this question has no answer. There's no number that you could add to another number to make it smaller. Or is there? This question makes no sense until we allow the negative numbers to exist, in particular -1 in this case. But if we allow the negatives to exist, if we give some meaning for that, then a bunch of other equations also make sense. Anytime I say a smaller number minus a larger number, it suddenly makes sense as well. So more equations become solvable. And subtraction can now be rewritten as addition. We take subtraction and instead add the negative of the thing that we are subtracting. And it turns out that addition has much nicer properties than subtraction, like commutativity, for example. And once we attach the negative sign to the 3 in this case, we can move this equation around, and it takes on a little bit more versatility. So it's better to write things with addition. It's good when we can give some kind of substance to equations which we might want to solve. And in this case, we wanted to solve things like this because of reasons like debt. If I have $2 and I take away $3, I still want to keep track of how much money I owe. And this gives a motivation for us wanting to come up with the negative numbers instead of just limiting ourselves to subtraction. Likewise with multiplication, we might want a way to get back from some number times some other number to the multiplicative identity of 1. And in this case, what would go here? Well, no number would make sense there if we only limited ourselves to whole numbers. But once we allow fractions to exist, then not only can we solve this equation with 1/2, but things like 2 divided by 4 or a smaller number divided by a bigger number also make sense as well. And division also allows us to rewrite division as multiplication. And just like addition and subtraction, multiplication has better properties than division does. You can do multiplication in any order. That's commutativity. It's associative. And so we generally would prefer to write things with multiplication for the purposes of solving equations and the like. Also, just like negatives could have a meaning in and of themselves, the quantities like 1/2 or other rational fractions might have meaning in themselves. For example, if we declare a unit size like 1 foot, well, yes, things like 1/2 foot totally make sense and might be something that we need in order to build our house. So we now have a way of describing those things by allowing the existence of other more abstract numbers than the whole numbers. So complex numbers are going to come up in a similar way when we try to work with squares. So for example, we might want to know what squared plus 1 is 0, or equivalently, bringing that 1 over, what squared is equal to -1. Now, this equation makes no sense as long as we limit ourselves to the real number line. And this is because squaring means times itself, but either 0 times 0 is 0, not -1. A positive times a positive is another positive, but also a negative times a negative is another positive. So it seems like something times itself has to either give us 0 or positive, but it certainly can't be -1. No real number will satisfy this equation, something squared is equal to -1. Now, if you're feeling a bit of resistance to the idea of just making up a number to go here, you're in good company, because historically, people rejected the ideas of complex numbers for a long time. Negatives really weren't as developed as a theory, even though they did kind of exist in the form of debt. Positive fractions were thought of as lengths, and length squared were thought of as areas. Negative area was rejected, and so the idea of needing a complex number was just rejected out of hand. It actually took many centuries and was part of the study of polynomials before people started to think, well, hey, maybe these things would actually be useful for solving problems. And that's exactly what happened. Complex numbers turned out to be great at solving problems involving polynomials. And their patterns and behavior, the algebra of the complex numbers and how they multiply and add to each other, turned out to be very similar to the way things in nature worked. Namely, how things called vectors add, namely, how things rotate and dilate. These patterns that we see in nature are mimicked by the complex numbers, or rather there's this wonderful miraculous correspondence between them. And so complex numbers turned out to be very natural as ones or positive whole numbers are, really, and they describe things in the natural world in the same way. And this gave some motivation for mathematicians and physicists wanting to include them and talk about them until, in modern day, they are absolutely indispensable. You can't do modern physics without them. So let's return to this generating idea. What squared is equal to -1? Now, you might think that you could fiddle around with some square roots and get some kind of an answer here, or at least an equivalent condition, and namely, whatever it is could be the square root of -1. Now, we've talked about how this maneuver of square rooting a square is a little bit tricky. We might have missed a negative solution here, but, this will satisfy. If something has this property that it's the square root of -1, it will satisfy the original equation. So, even though we might have missed a solution here, and we will come back to that, what we will do is define a number by this property, that it is the square root of -1. And that number gets its own symbol to designate it as not being a real number at all. I know you're used to letters being variables in mathematics, but there are several letters, E, pi, for example, and also this one, I, who are constants. They are defined to be a certain number. And this funny little equal sign with a colon on it means defined. There's no reason that it is equal to -1 or the square root of -1. I'm saying it is. I'm saying that is what we're going to call I. It is the square root of -1. And so sometimes mathematicians will use this definitional equality when it's not equal to that for some other reason. It's just the definition that I'm making. Now note that that would mean, squaring both sides, that I squared is equal to -1. And these are the two main properties of I that you must know. You must know that it is the square root of -1, and if I square it, I get -1. And this is definitely kind of a weird looking number. I'm not saying it's not. It is called the imaginary unit I. Imaginary is perhaps not a great term for this. It's just what we happen to call it in the popular jargon. In fact, I think it's just as real as any other number. It just isn't a quote-unquote real number in the technical sense. It's something else, not on the number line, but adjacent to it. The main thing you need to keep in mind are those first two properties. It is the square root of -1, and if you square that number, you therefore get -1. So it's worth mentioning at this point that we did in fact miss an answer to the equation x squared is -1. The negative of I, the thing you would add to I to get 0, is also a solution to this equation. And this is because if I square it, the square distributes against the -1 and against the I, and that gives me -1 also. All of the properties of exponents and all of the properties that you're familiar with from algebra are also going to apply to I and the complex numbers as well. Now, this negative I is actually pretty important. It's called the conjugate of I, and in the next few videos, we'll come back to conjugates and see why they're important. But for right now, we should just note that there was this additional solution of negative I that we could have gotten to this equation. Why are we going to be studying this? Why are complex numbers so useful? Well, the idea in math of will I use this, right? Is this going to affect me in my life? It really depends on what you do with your life, right? It depends on if you get into something where you would need the complex numbers to describe the patterns you see. That might not be the case, but they are central to our algebraic theory, and that's one of the reasons we're studying them. What things do they do? The multiplication of complex numbers describes spiral motion. Addition and subtraction of complex numbers describes two-dimensional vector addition. You can represent wave behavior or periodic behavior that has amplitude and phase and all that by complex numbers. And this is one of the reasons that they are central to our modern physics, central to understanding quantum mechanics. Even outside of that crazy space, all polynomials, which are sort of like constants times variables to powers added up with one another, these kinds of equations have exactly n, where n is the biggest exponent, solutions in the complex numbers. And so even though we're going past squares to third or fourth or nth powers, we don't need new numbers to solve those. All you need is the complex numbers. They fix the whole problem with sort of exponents and what their solutions are. So we need them, not just to talk about the solutions of exponents, but the solutions of polynomials, which we'll talk more about in the next section. The complex numbers and their behavior are also backdoors to lots of other problems in math, problems in calculus, even problems involving prime numbers and number theory. These things use the patterns of the complex numbers to sort of sneakily attack different problems. And there's many other applications, but we'll look at one more in particular. For now, we're just going to look at how they can help us simplify radical expressions. Odd indexed radicals, like 3, 5, 7, and so on, we don't really have a problem with negative radicands here, negative arguments. That's because a negative number multiplied by itself an odd number of times will give me this negative number. Negative 2 times itself 3 times gives me negative 8. There's no problem with producing a negative here, but pairs of negatives become positive. And that means that if there's a negative argument here to this even indexed radical, and there's a little invisible 2 right here for square roots, right? That means that normally, for real numbers, we wouldn't have an answer to this question, what is the square root of negative 4? But because we can break that negative piece off and just look at the 4 and the negative 1 separately, and now we have an answer to what is the square root of negative 1, it's I, we can actually rewrite this as a number without a radical. This is just 2I. And that's really all you have to know about how to simplify radicals. If there's a negative under this even indexed radical, you pull its I out. And you just pull that out, and then you deal with the positive part the way that we did in the previous videos. So here's some critical notes. I want you to copy this as proof you watched the video. Show it to me later. What is I? By definition, it's the square root of minus 1. What happens when you square it? You get minus 1. If I have C a positive number and I'm looking at the even radical of negative C, well, the negative part comes out as an I, and then you just take that even radical the way that you normally would. This works for square roots, it works for fourth roots, sixth roots, eighth roots, and so on. All right, time for some practice exercises for the day. First one is I want you to consider the powers of I. Multiply I by itself 3 times. What do you get? 4 times. What do you get? 5 times. What do you get? Do you see a pattern developing? If you see that pattern, describe that pattern, and then use that pattern to evaluate I to the 101. Problem number 2, I just want you to simplify these radicals. Square root of negative 9, negative square roots of negative 100, and the square root of negative 12. Pause the video at this time. All right, let's see how you did. So it's actually helpful, I think, before we begin to write the 0th and the 1st power and the 2nd power of I. This one I gave you in the video, but I also said that all of the exponent properties still hold. I isn't 0, and so its 0th power is 1. Anything to the 1st power is itself. I squared is negative 1, and I to the 3rd power is I squared times I to the 1st power. I squared is minus 1, and so I times minus 1 is minus I. 4th power, well, that's just I squared times I squared, and so this is minus 1 times minus 1, which is positive 1. Positive 1, we got that before. What about I to the 5th? Well, I to the 5th is I to the 4th times I to the 1st. Well, I to the 4th we just found out is 1, and 1 times I is I. Okay, wait a minute. There's a pattern here. So it goes 1, I, minus 1, minus I, 1, I, minus 1, minus I, and so on. So really there's this four-fold pattern, this pattern that repeats every 4 steps. And we could figure out what step we were at by looking at these exponents and dividing them by 4. These are the remainders when I divide by 4. 4 divided by 4 is 0 in remainder. 5 divided by 4 is 1 in its remainder, and it is the same evaluated value as I to the 1. So we can encode that pattern this way, where C is some positive integer. If I get 0 when I divide that by 4, then the answer is 1. If I get 1 when I divide that by 4, then the answer is I. If I get 2 when I divide by 4, the answer is negative 1. And when I divide by 4, if I get remainder 3, the answer is negative I. And so now we know what to do with I to the 101. All I have to do is divide it by 4. I get 25, because that's 4 times 25 is 100, and then 1 more. So remainder 1. And so if this is remainder 1, I get I itself back. So I to the 101 is just I. By the way, this pattern of exponents also works if we kept going into the negatives. What is that? It's 1 over I for I to the negative 1. If we multiply on the top and bottom by I, we get I squared on the bottom and I on the top. I squared is just minus 1, and so this becomes minus I, which was the next one in the pattern if we went backwards here, right? If we went from the red to the yellow, we should get minus I. And so in general, we could extend this to the negative exponents as well. Just worth noting. Okay, what about problem 2? Problem 2 is square root of minus 9. That's square root of 9 times I, or 3I. Negative square root of negative 100. Well, bring that leading negative outside. The square root of negative 100 is square root of 100 times I, which is 10I. So this whole thing evaluates to minus 10I. For this one, we really need to know what is the square root of 12 simplified, because the negative, we just pull the I out. Square root of 12 is the square root of 4 times the square root of 3. Square root of 4 is 2. So the square root of 12 is 2 radical 3, which we could write this way. Now, it's customary to put the radicals at the end sometimes. You can put these less complicated numbers up front. And yes, I might look a little freaky, but it's definitely less complicated than the square root of 3. The square root of 3, we talked about why irrationals are so weird last time. There's something that can only ever be approximately known in any finite sense. We can understand perfectly what that is. Now, that being said, it's also totally fine if you want to put the I on the end. This actually accords better with something called the standard form for a complex number, where we write its coefficient as a real number, and then we write our I. Both of these have their pros and the cons. We'll talk more about standard form of general complex numbers in the next video. That's it for this video. Thank you for your patience and have a great day. Good luck with your studies. I'll see you in the next one.